star in the foreground and another star whose light travels to Earth. If this star is off this line of sight, you're going to see double images. And this is something that he did not believe you would be able to see in reality, but he saw that at least part of the consequences of general relativity is that you should be seeing things of this sort. In the essay, he went on to observe that if the source sits on the line of sight, it will appear as a formally infinitely magnified ring, which he also felt should be highly unlikely. Today, we call it an Einstein ring in his honor, and I'll quote, he said, "There's no great chance of observing this phenomenon." And in fact, he was referring to that and the other. Nonetheless, the story I will tell you today will be as follows. As mathematicians, we like to build theories, and I'm going to build I won't give you the whole theory, but I'll give you a portion of it, a theory around this example. And we'll be interested in multiple images and this phenomenon where you have formally infinitely magnified images. Just as a hint of some terminology, that's called a critical curve. And the position from which you have formally infinitely magnified images are called caustics. So in his example, you have a point caustic, and the critical curve is a circle. Okay? Now, to set up the machinery to describe this theory, one will need some assumptions for your particular cosmological setting. And here are the two, I would say, driving assumptions of most of standard gravitational lensing. First, you assume that the lens is thin, and by that I mean its diameter is very small compared, say, to the distance from Earth to the lens, or from the lens to the light source. That's called a thin screen approximation. We are then allowed to treat the lens as if it's lying on a plane. The other assumption is we'll assume the bending angles that are being created, so these deflection angles here, are small. By that I mean significantly less than 1. Now, of course, an exception to this weak field assumption is already a black hole, and I would be happy to talk with you about that during the Q&A. But black holes can have bending angles that are any integer multiple of 2 pi, for example. Now, in order to set up a model that is driven by these two assumptions and that can address the issues Einstein raised in that essay, we need a mathematical model of the space-time neighborhood in which all of this is happening. So you have to imagine a thin strip of the universe where there's a lens and a light source. We'll be able to ignore the rest of the universe for the most part. Mathematically, it ends up being a Lorentz manifold where this product, I, is an open interval that will carry a sense of cosmic time, and S will represent space. For our purposes, it would be an open subset of Euclidean 3 space, unit 3 sphere, or the unit hyperbolic 3 space. And the Lorentz metric has this form. Now, the way you could think about this intuitively is as follows. If this term phi is not here, you get the standard Big Bang cosmology metric, where the function A will represent the expansion in the universe. So this piece gives you the metric on space, and that gives you the rate at which it's expanding. And here, that's a standard metric on the spaces I alluded to earlier. Phi now will represent a perturbation to that Robertson-Walker metric. So intuitively, imagine the following. If the universe without a perturbation is treated as this metric without phi, think of a sandbox where the sand is smooth. And then you create a little hill. The perturbation due to that hill is being captured by phi. And so I'm thinking of phi as a potential that models the presence of a positive perturbation. You could create a little hole, and that will also be a perturbation. But for today's talk, I'm not going to discuss that. Now, here's a schematic of what I just said. In a space-time picture, you imagine that here we are, say, in our galaxy, because that's a scale we'll be working at in some context, and you have a whirl line. A point on this line gives you your cosmic time and your position in space. Now, imagine a light source here, and let us say there's no lens between you and that light source. A light ray travels towards you, and it meets you here at some later cosmic time. It'll go along the dash path. If you insert a lens, and say the lens will be represented by that line, which in these dimensions would be a plane. Remember, I told you it's thin. So the light ray gets deflected at the lens plane, as in this schematic, and arrives at the observer, notice, later. And so there's a time delay due to the presence of the lens. It's that time delay we're going to try and calculate. I'll only mention at this stage that this path can be modeled by a piecewise smooth null geodesic. And when you project these two paths down into your standard space, remember what S is, either our open set in R3, S3, or H3, you end up forming a geodesic triangle. And the idea is then to figure out the difference between these two lengths in those different geometries. Now, you have to be careful when doing that because the universe is simultaneously expanding. And the full derivation of this time delay is done in Chapter 3 of the book, finished last year with Levine and Vamsgans. It's a rather lengthy and delicate calculation in general relativity, but fortunately, it is doable. And so the idea is we get at this time delay by looking at the arrival time of the lens light ray minus the arrival time of the unlensed ray. It turns out to have an expression that looks like this. It's a little complicated when you have all these terms in here. But the thing you should just keep in mind is that it has a quadratic piece, and then you have a piece here that's coming from the lens. That psi is an integral over that potential that we had in the Lorentz metric from the previous transparencies. This Zi, that's like redshift, Di's are distances between the lenses and so on. So it's a quadratic plus a potential piece. Now, once you have that from the physics, you want to work in dimensionless variables because, you know, in order to start to prove theorems about this, you have to be careful to not have your quantities in physical units. So let us simplify the expression you just saw. And I will, you know, scale things as shown. Intuitively, the xi's and the y are going to be angular vectors on the sky. Y in particular will be angular position out to the light source. Xi will be on the ith lens plane. And then this was a little too yucky and call that psi sub I. Then the other mess, the theta i's, you'll think of as involving distances, similarly with the betas. And you simplify the time delay function as follows, having it in dimensionless vectors. Okay? Good. So imagine that you get this from the physics, and now we want to start a rigorous mathematical model. So let's start all over again. And I'm going to tell you what I mean by a potential for the lens. First of all, let us consider the plane minus a finite set of points, which will be represented by A. Oh, thanks. Yeah. Right. So by a gravitational lens potential, I simply mean a C infinity function on this set whose Laplacian is never negative, and such that whenever you approach an element here, either the potential goes to minus infinity, or its Laplacian goes to plus infinity. And that simply is telling you we're only going to look at two types of singularities in this function modeling the lens. That, I have physical reasons for doing that, and I will give you an example in a moment that fits this. I'll tell you that this formal abstraction fits every known physical model for gravitational lens potential. And if you want, you can be more precise and say what a lens plane is. It will be the domain of that mapping. And alpha, I'll take a shorthand for the gradient of the potential modeling the lens. Physically, that will turn out to capture the bending angle of the light rays. And now, for example, when A is the empty set, so there are no singularities, we'll call the potential non-singular. Here's an example of a potential that models local regions of a galaxy. You imagine that you have a collection of point masses. Those are the stars, so you'd have G stars. That piece of the potential, for physical reasons, looks like a logarithm. Whenever here, this is a position of the Lth point mass. You see you pick up singularities when X approaches a point mass position. And this term you could think of as arising from the tug of the rest of the galaxy. So you're looking at a small patch of stars in a galaxy, and gamma will be the external shear from the rest of the galaxy. The kappa C will model the interstellar matter between the stars in that local region you're looking at. So here is an example where you're going to have G singularities. You could then go back and formally define a time delay function where you use the potential on the left as the input. So as mathematicians, we always abstract. We'll now go from the beginning and define a k-plane time delay function induced by these potentials, by these lenses on the different planes, to be a function that has the following form. And we got that right out of the physics. And of course, this induces a family of function parametrized by the light source position. Okay? Now we have our hands on the time delay function, and we want to talk about the geometry of gravitational lensing. One of the first things that we will need to know how to do is to say, what are light rays? Well, a light ray, its definition will be motivated by Fermat's principle. And this you may remember from elementary optics in high school or freshman physics. And the idea is that light rays will be those paths such that these impact points form critical points of the function, of this time delay function t sub y. So the light rays will be characterized by all solutions x of these k vector gradient equations, right? We'll say light of ty will be the set of all light rays of the time delay function. So now, with this done, you can get a picture, at least abstractly, of how to represent the light rays. They are going to be the critical points, the saddles, the minima, and so on, in the graph of this function. We'll call the graph a time delay hypersurface. So, for example, a global minimum in this graph and a global maximum will correspond to light rays that arrive first and arrive last, right? So you're now reinterpreting the light rays in terms of this abstract surface here. Interestingly, you will also see that the geometry of this surface will relate to properties of the images you're going to see on the sky. And I will show that to you in a moment. But for now, you're imagining the light rays are being captured by the critical points in this hypersurface. What I just did was to give you gravitational lensing through this arrival time point of view. We have characterized light rays. Now you can also look at it from ray tracing. And the way that goes is as follows. If you imagine now sending a light ray backwards from the observer to the light source plane, it will impact at different points on these lens planes and land somewhere, right? So you're inducing a mapping from an open set in its first lens plane into S, the light source plane. Just tracing the light rays through and having gravity bend them induces a mapping. it turns out you can actually write out an explicit expression for the mapping that the light rays induce. It looks a little nasty, but here it is. It's defined recursively as follows. We call it a K-plane lensing map. And the thing to remember here is that this eta I is the mapping induced by following light rays and stopping at the ith lens plane. Okay? And alpha I will be the bending angle at the ith lens plane. Notice if there's no gravitational lens, the alphas will all vanish, and you'll get the identity map. So the presence of gravitational lensing induces a lot of non-linearity here on the right. Now, when we speak of lensed images, it's what you're seeing along a particular direction. And so that will be solutions of this equation. Here's y. Eta is the mapping that takes you into y. It'll be solutions on this first plane to y equals eta of x. And the reason you select them on that first plane is that when I'm here looking, the lensed image I'll see along that direction. And so this induces the images I see on the sky. Okay? And so this is now a different point of view. I will now link that back to light rays. When you have images on the sky, you will want to talk about the brightness of an image. And this is how the brightness is defined via the lensing map. It is 1 over the determinant of the Jacobian of eta at the lensed image. So remember, x is a solution of eta of x equals y. Physically, that is simply the flux of the image divided by the flux of the source in the absence of gravitational lensing. So it's comparing the two. When you have then a magnification greater than 1, you'll see that the flux of the image exceeds that of the unlensed source. And so you will say it's magnified. Less than 1 will be demagnified. Now, what is the link between this point of view of lensing and the arrival time perspective? It's contained in the following theorem, which is given in chapter 6 of the monograph. The first thing is you have a bijection from the set of all solutions of the lens equation and light rays. In other words, I have all these critical points in this hypersurface here, and then I have these lensed images, solutions of this two-dimensional equation, and there's this nice one-to-one correspondence. When I then look at an image on the sky, I can identify it with, say, a minimum in this hypersurface. For example, it turns out that minima, if you look at minima, they can never be demagnified. And that conclusion you draw not from the point of view of the lensing map, but from the point of view of the hypersurface. And it will end up putting upper bounds on the Gaussian curvature, Gauss-Kronecker curvature in that hypersurface. And here's what the exact relationship. The magnification of a lensed image is inversely proportional to the Gauss-Kronecker curvature at the corresponding critical point of the time delay hypersurface. Here's magnification, there's the Gauss-Kronecker curvature. And so the flatter that surface is around a critical point, the more magnified the lensed image is going to appear. In fact, you can even go a little deeper into the geometry and look at things like umbilic points that will correspond physically to lensed images that have no shearing in it, and so on. But the idea is that you have this very nice way of interpreting some of the observable properties of a gravitational lens system. Now, in the essay Einstein had, he counted multiple images, and I'll give you some results that are universal in the sense that it does not depend on the particular choice of your model of the lens. The idea is that you have a lot of debate as to what is a good model. And mathematics is well suited to give you these generic results. Let us set it up as follows. We'll make two assumptions. One is that the singularities of the potential behave in this way. The potential goes to minus infinity whenever you're approaching the points in that AI we saw at the beginning. An example of this is that point mass potential that I showed you earlier. We'll also assume the lens is isolated, so there is nothing else around it. And what that converts into is that the time delay surface is going to climb up when you go far away. Okay? Under these two assumptions, we'll set up some notation where GI will be the number of singularities on the ith lens plane, and n plus or minus will be the number of even or odd index critical points in that time delay hypersurface. One of the first results I did in gravitational lensing was the following theorem. And I worked on this problem because an astronomer at the Institute for Advanced Study then said, well, how many images would you see if you have a star on each lens plane? And he said, if you have k lens planes, you should see 2 to the power k. We said, but intuitively, I don't know what happens. I can only give you a lower bound. And I was so gripped by this problem. And I'll show you at least what I think is among the most general thing you can about such a system. The theorem states that there is an open dense subset of the light source plane such that the total number of lensed images of a light source at any point in that set obeys the following counting relations. For example, the total number of lensed images is twice the number of even index ones minus this product. And you have a companion result for the odd index ones. Observe that if there's one singularity on any lens plane, this whole product vanishes. And so you get an even number of lensed images. Here's the general lower bound on the total number of lensed images you should expect. If you have 1 point mass on each lens plane, average GI is 1, you get the 2 to the k the astronomer was talking about. So that was quite good. His intuition, I think, was quite accurate. Interestingly, if there are no singularities, if all the GIs vanish in this equation, you're going to get this expression here. And so you're going to have an odd number of lensed images whenever you have a transparent lens. Observationally, you will see an even number. And the reason is that the odd guy ends up being a maximum. And you can show a maximum has to be located in the densest part of a deflector. So it would be near the nucleus of a galaxy. So there's a lot of obstruction. And it'll end up being demagnified. And so mathematically, the Gaussian curvature ends up being very high in the vicinity of maximum images. The strategy of the proof is as follows. You use the theorem here that gives you this bijection, and that's this relationship here to identify solutions of the lensed equations with critical points of a time delay function, and then you import the Morse inequalities to get these counting formulas. That's the general idea. Fortunately, for gravitational lensing, you can compute all the homology groups. And it's a very nice exercise. I always give it to students in my course on gravitational lensing to calculate all the homology groups. And they just have fun doing that. And they can then derive out these counting relations. A detailed proof of this result is given in these chapters. And I should add, you can then do the same thing without these two assumptions. You can do it for the most general type of singularity you could imagine. but this is the fastest way to state the results. So this is like the companion to the double image result that Einstein found, and it applies in particular to any number of point masses. It doesn't even have to be a point mass type singularity. Next, I want to give you a feeling for how do you tackle this idea of this Einstein ring, right? You want to make sense of those concepts, first of all, in a coordinate-independent way, and then trying to get your hands on what is really going on theoretically. Well, the natural thing to do is to define critical points of your lensing map to be places where the rank of the Jacobian matrix drops. In other words, this will be where the determinant of the Jacobian matrix vanishes. Whenever these critical points form curves, we'll call them critical curves. They may or may not form curves. Generically, we shall see that they do form curves. Physically, the set of critical points will then correspond to all the formally infinitely magnified lensed images for every light source position. And that's because the determinant is vanishing. And remember, magnification is gives you 1 over that determinant. Caustics will be the critical values of eta. And we know this is a correct definition because physically, it'll correspond to positions from which a light source has at least one infinitely magnified lensed image. And so you can, for example, make some general observations immediately that caustics will always have measure 0 by Sard's theorem. You can quickly conclude that the set of critical points will be closed in the domain of eta, and so on. Pictorially, this would be sort of what you're seeing. The critical curves are here. The caustics are back on the light source plane. Now, I would like to focus on 2 extremely important critical points. These are the folds and cusps, and there's no easy way to define them. I will at least to define them without using coordinates. I'll give you the definition, but then give you a picture how to think of it, because it takes a bit of machinery in order to get the definition right. So you consider a C-infinity mapping between 2-dimensional manifolds. And I want to now identify a subclass of critical points of that mapping. These will be the transverse rank 1 critical points. So it'll be all points where the rank is 1 of the Jacobian matrix. And then the one jet is transverse to this singularity S1 at that point. So there's a transversality condition you're including here. It turns out that these conditions together make this set of transverse rank 1 critical points simple. They are diffeomorphic to a union of disjoint circles and or real lines. And so they're not hard to see visually. Now, in order to define cusps, you can do it using transversality statements, but I thought it might be a bit easier to do that in the following way. So this is somewhat a different twist on it. For each transverse rank 1 critical point, you could show that there's a smooth non-vanishing vector field on an open set about the transverse point. And I'm going to remember they're curves, and I'm going to have this open set intersect only one of the components, only one of the curves. So this vector field will have the property that each of its vectors lies in the kernel of the differential mapping at P. And this will happen along that component of the curve in the open set. The other thing is there's a smooth function J on this open set so that it vanishes along that curve, and its differential at the transverse rank 1 critical point is non-zero. So this may sound a little technical, but embedded in it are some natural transversality statements. This then is how you define folds and cusps invariantly. Consider the function induced by this vector field acting on J. X will be a fold critical point if X is not a zero of the function. And it will be a cusp critical point if it is a simple zero. So not just a zero, but a simple zero. So you have to require that the differential map at X is non-zero. You can show that these conditions for folds and cusps are independent of the choice of the vector field and of the function J. A complete proof of this is in section 7.5 of the monograph. So you have this somewhat abstract invariant way of getting your hands on it. This formulation has its own advantages, which I won't be able to go into right now. But here's something that is more clear intuitively. Whitney classified folds and cusps using coordinates. He basically said that X will be a fold critical point if their coordinates lambda and eta such that it has a simple form. Notice that's just a quadratic. So this will give you the behavior of the mapping in the vicinity of a fold. For the case of a cusp, the coordinate expression has a cubic here where A and B are plus or minus 1. Okay? And we also give a detailed proof to show the equivalence of those two formulations. Now this is so simple, you can draw a picture of that. And I'll show you it. The first one, it'll tell you that the mapping behaves as follows in the vicinity. So here's a fold critical point, and this is a little neighborhood around it. So imagine you're dealing with a lensing map. This is a little patch on the first lens plane. The first thing it tells you is that there is a critical curve passing through it where all the neighbors, everything on either side of this point, is also a fold critical point. And what it does is it folds it up, as the name suggests, and then projects it down, squishes it down into the light source plane, creating this caustic. So notice that if a light source crosses from here to here, locally you have two very bright images abstractly sitting on this surface. When you cross out, the two images disappear. They merge and disappear. In the case of the cusp, you could show that the critical curve has this form. Here's a cusp critical point. And all the other points on this arc are folds. So it's abutted by fold arcs. It then pleats this little patch as shown and projects down to a cusp abutted by fold arcs. Observe again that if a light source sits in here, you're going to have three very bright images that are close to each other. And when you cross out, you're going to have a merger of two of the images, and you lose two, coming down to one. And that's locally. So the idea is that the fold gives you two bright images, and the cusp, three. And that's locally. But it's always nice to go from the abstract invariant formulation to something that's easy to visualize. There's one more piece of the puzzle, and that has to do with stability. We are not interested in just genericity, but those properties that are typical and also stable against small perturbations. It's not that easy to define stability without a lot of machinery, but I'll try and give you a shortcut here. We let F be a C-infinity mapping between manifolds, and we look at the germ of the mapping at X. Intuitively, you're just localizing the mapping at that point. We'll say the germ is stable if for any neighborhood U of X, there's a neighborhood script F in the space of functions about little f, such that for each mapping in script f, there is a point near the original 1x, basically, such that the germ at that point is differentiable equivalent to the germ of f at x. We will then say the mapping is locally stable if its germ at every point is locally stable. It is stable. Intuitively, what this means is that for any point in x, there's a sufficiently small perturbation of it such that there's a point x tilde near x where the perturbation at x tilde is differentiable equivalent to f at x. There's a cautionary remark to be made here. Oftentimes you'll hear astronomers quote the result that, well, if you have a lensing map, local stability is generic. You just perturb it and you get a locally stable mapping. You have to be careful because if you perturb it, yes, you may get a locally stable mapping, but that mapping is not guaranteed to be a lensing map. You have to perturb within the space of lensing maps. And you know that can give you a totally different classification. Okay. Whitney classified the locally stable mappings in 1955. He showed that they're the ones such that each point is either a regular point, so that's a point where the rank is full, it's at 2, a fold, or a cusp. And that was why I focused in on folds and cusps to begin with. And so you see, these are, at least from the point of view of stability, the right things to look at. I will now tell you about the genericity aspect of it. How typical are these mappings? If you let M be the space of k-plane time delay families, where here I'm assuming that the potential is positive when you have the potential at 0. I mean, that is something you can physically always get rid of by adding a small, low-density interstellar matter. And so you can always, for all practical purposes, assume that. The natural topology you put on a space of function in this context is a Whitney C-infinity topology. That's extremely fine. And then M star will be the subset of time delay families whose lensing maps are locally stable. It turns out that this set M star is open and dense in M. And so this thing just fills essentially the space of all time delay families. And so any theorem you prove about locally stable lensing maps will carry generic properties about any physical gravitational lens system on the thin and weak field lensing. The proof of this involves a lot of technical transversality arguments to stratified subsets of jet bundles. And if you like that kind of stuff, you could look in section 8.4 of the monograph. So you see, it took a lot of machinery to just draw the simple conclusion that local stability is universal among gravitational lens systems. So folds and cusps, we expect to see them essentially everywhere in physical systems. I will now show you some pictures from numerical simulations. Here are caustics due to a few hundred point masses. The white curves are the actual caustics. For example, the color shading goes as follows. A source here is less magnified than one in the green. The red is more magnified than the green, etc. And so you have, in a sense, you could think of this as the shadows being created by the point masses in a distant part of the cosmos, right, around where the light source is located. And
I understand, right, this is a picture in the source plane.
That's right. That's right. And here is one due to several 100,000 point masses. The thing, whenever I look at this, I think of two things: a neural network in the brain and a large-scale structure of the universe, where it's all optical. This is now, remember that point mass potential I showed you? It is that where G is, I think, like 200,000. and the shear, as you see, is acting along the horizontal. If you look in this little box, you get this. This box is magnified to that, and that little box is here. And so deep inside that network, you still see folds and cusps. And at least I think visually I'm convincing you that this is generic, it's universal, and the theorem is correct, right? I will now show you one more example, and this I find this example rather profound. I showed you caustics due to a singular lens. The singularity is coming from the point masses. Here's one due to a transparent lens. And remember I told you should have an odd number of images? Well, on the left you're looking at the caustics, and on the right the critical curves. You may notice that dot. It's not a smudge. That's a tiny critical curve. Inside there, there's a fifth image, but it's extremely demagnified. And so for all practical purposes, these four will dominate whatever you see physically. This outer critical curve goes into the inner asteroid, and that little one there goes to the outer elliptical shaped caustic. Now, remember I told you that for a fold you have a pair of close, bright images? Well, here they are. And for a cusp, when the source sits on a cusp, you have the triplet, close, bright images. When it's near the center, you have this sort of configuration. Now I'll show you observational data. This, you can actually see this at the Castle's website, at the Harvard-Smithsonian website. This is actual data. Look at that. And look at this. Right, this is observational example where you have the close image pair where the source is sitting on a fold caustic. I'll show you an observational example. Look at that. Isn't that amazing? It's sitting on a cusp, right? This overall same idea, right? Of course, when you're modeling that, you're going to fine-tune this more precisely, right? Here is an example of the latter one.
This fits one lensing plane.
One lensing plane, that's right. One lensing plane.
And are we seeing that extra source there, that white dot, or is that?
This one here?
Yeah, right.
Yeah, that's from the deflector galaxy. Yep. And notice the bar gives you 1 arc second. Here is an example of the last configuration. And this one is called an Einstein cross. And that's 2237. It's quite remarkable how successful these models are. Right? I wouldn't have believed it unless. So that gives you a rough and quick feel, I would say, for how one could abstract that essay that Einstein did to general gravitational lens systems. Now, I have about 15 minutes left, and I thought I'll do an application, leave the abstract math alone, and say, okay, I've convinced you they look alike. There's something we're doing correctly. But let's make a prediction. This part of the talk, and I may have to skip some parts, is based on work I just did with an astronomer, Scott Gowdy at the Institute for Advanced Study. They're in 2 papers in the Astrophysical Journal. This one will be appearing next month. So in this paper, we are assuming a single plane lensing situation, and we're going to make a prediction based on some of the mathematical machinery we had in the first part of the talk. But before doing that, why don't we take a look at that essay Einstein wrote and try and rederive what he did, but from a 2002 point of view? Well, this is how you would do it. You are given a potential, that's a point mass. You write down the lensing map. You write down the lens equation and solve it to find the lensed images. First, you assume the source is not at the origin. Remember, you had the source off the line of sight. And using complex variables, you can quickly solve this equation when you set it to y. You find there are two solutions of that form. You could show that x plus is a minimum in the time delay surface, x minus a saddle. The magnifications of the images look like that. They obey this universal difference relation. You can show that the minimum will always be magnified. And you can also quickly calculate the critical curve and caustic. That will be the case when y is 0. You'll obtain that the solutions are given by magnitude of x equals square root of m. That's the equation of a circle. That's your Einstein ring. If you map the circle under the lensing map, so you take this and plug it in here, you'll get 0. And that's the point caustic that he found. Okay? And to summarize, you'll see that you could draw a very nice picture of what's going on due to a point lens. You have a point caustic. This circle is the Einstein ring. You have a lensed image outside, one here. This is the case when the source is sitting, when the source is at the point caustic, you get a critical curve. Okay? I think you'll quickly see what he did was not locally stable. Yeah, and it shouldn't surprise you because it has all this symmetry, right? When you perturb, you break all this symmetry. But he wasn't way off in that if you perturb the system he looked at slightly, say with a shear, his point caustic becomes a little asteroid, an extremely tiny asteroid. And you'll still get this overall general result. Okay? Now, there's a point I want to make here. You could think of the diameter of this ring as roughly, we'll be an astronomer for a moment, giving the spacing between these images. Because the closer the source is to the caustic here, the closer these images are to that ring. And so the angular radius of the Einstein ring is an important quantity. You can write out the formula for it in detail. It looks something like that, where ml is the mass of the lens, and these are the obvious distances. And so we think of the angular Einstein ring radius, again, as inducing roughly the angular spacing between images. When you look at our local group of galaxies, this is like the 20 or so galaxies, including ours, that are gravitationally bound. You plug in the usual values here. You'll see the Einstein ring scales as 1 milliarcsecond times this quantity. An arcsecond is a small angle. If you have a ruler that's the average, say, Earth-Sun distance, and you put that ruler at 3.26 light years away, the angle it subtends is 1 arcsecond. And we have technology that can really deal with such small angles. In the case, if you let m with this circle dot as the mass of the sun, if your lens is a star with roughly the mass of the sun, you plug that in here, this is 1. And so you find the angular Einstein ring radius about 1 milliarcsecond. That, unfortunately, is outside the optical resolution of current technology. The best we could do in the optical is about 100 milliarcseconds. In the near future, though, NASA will be launching a satellite called the Space Interferometry Mission. That'll be in 2009. That's expected to improve down to 10 milliarcseconds. Now, there is an area of gravitational lensing called microlensing, where it's a situation where you cannot resolve the multiple images. where the spacing between images are too small. In other words, for today's point of view, below 100 milliarc seconds in the optical. But there are two observables you can have. One, it's called a light curve, and that's a plot of the total magnification of the lensed image as the source moves, because everything is in motion, right? Relative motion. That is accessible to current instruments. And the way you think of it is you'll have an image on the sky. It's built out of a lot of tiny images. We can, however, see the total effect of all these images, and that is the light curve. There's another quantity called the image centroid, which is the center of light of all those tiny images. That is expected to be accessible to SIM, which will have an amazing positional accuracy, which is different from angular resolution, of a micro arc second. And so whatever prediction we make, we have to make sure it's within that particular case. So the goals in the two papers was to develop analytical expressions for generic behavior of the photometric, that's the light curve, astrometric, the centroid, behavior of extended sources, right? All the theory I spoke about assumes the source is a point. Realistically, it will be you could treat it as a little disk. Since this part is already known, we decided to predict the generic shape of the astrometric curves for an extended source. So let me I'll keep that up for now. There's one piece of notation that I need to run you through. In microlensing, it's convenient to further scale that x by the angular Einstein ring radius and the y by the same. And so we relabel them as shown. So theta will be the angular position of the light source and of the image, and u the angular position of the light source. In single plane lensing, the lensing map has a simple overall form. We will let μi be the magnification of the ith lensed image. And so mu tot will just sum over all these magnifications. T will simply be capturing the motion of the source as a function of time. And typically, the source will be moving at constant speed. So you have a rectilinear motion. This is the new quantity. The centroid, or center of light of all the images, is defined in this way. Mu I is the magnification, theta I, the angular position of the image, and that is the total magnification. It looks just like the definition of a center of mass, right? You replace mu I by mi, and so on. But there's a big difference. In gravitational lensing, pairs of solutions can suddenly disappear and appear. In the center of mass, the objects don't suddenly disappear. And so you are going to pick up a lot of singularities in this path, right? And so you have to be aware there's a strong difference. Since everything is in relative motion, this will be the quantity you're going to see, theta I minus the motion of the source. And remember, we divided by theta e, so you have to multiply back by theta e to get the observable. And so SIM is supposed to be able to measure that. Now, we are going to build we are mathematicians, and for us, that's just a straight line. It's rectilinear motion. So this is the meat of the matter. And so it suffices to study theta CL. It will turn out that when you're crossing a caustic, you're not going to see much difference between delta theta and theta CL. This is a theorem you need to be able to make it happen. I'll tell you it quickly. It tells you basically that you can approximate a locally stable lensing map in orthogonal coordinates by these two polynomial forms. This formula was arrived at by Schneider, Ehlers, and Falco, astrophysicists, in 1992. And they use different coordinates in the lens plane and the light source plane and a string of heuristic arguments. So Levine, Wamsgans, and I decided to redo that result and cast it in the language of local stability. And we showed that you can use a single coordinate change in the same coordinate change in the light source and the lens plane and arrive at that same form. And we gave a proof using transversality arguments. And so I'm quite confident that is correct now. Okay. The difference between this and Whitney's theorem is we are giving a quantitative now, not qualitative, indication of how the lensing map ought to behave. So what do? You now have a form for your lensing map, and that exercise I went through with when we relooked at Einstein's essay, you do the same thing. You calculate the images, the critical curves, magnification, and so on, except you have to do it over an extended source. And I'm not going to take you through all of that because it's just a royal headache. But I'll give you a feeling for something interesting that happens. When we did that, two series of integrals emerged. And I just want to know if anyone has seen these before. Let's talk after my presentation. This is what they look like. I mean, these things we abstracted them into this general form. But these things started appearing. This is a Heaviside unit step function. And that's a regular one-dimensional integral. So I don't know if anyone has seen this before, but they emerged out of our calculations. Another thing that happens when you look at the case of the cusps, I'm only talking about the folds for now, you end up getting a four-family series of integrals. Two associated with the symmetry axis of the cusp, and another two with the axis perpendicular. And I can show you those if you're interested. Well, I'm going to skip and give you a picture of the answer. Here you have the fold caustic you get out of that approximation. And imagine a disk light source is traveling across it. It hits it there. This point over here is the critical curve. This point goes to there. And you have the two images that merge at the critical curve. So you now imagine, because you're near this caustic, you have these two bright images that will dominate the behavior of the lensing. And then you have other images far away. The center of light of the remaining images you could imagine as drifting along here. But here's the predicted centroid. I'm going to skip all that. This is the answer. We find that as you're going across this caustic, the centroid moves this way and then accelerates that way and goes this way. Okay? So let's put this over here. Right, we have an exact formula for this curve. Now, we don't want to wait until 2009 to find out whether we are wrong or not. And so decided to take known data of gravitational lensing where the light curve was observed. They found a model that fits the light curve, and then take that model and calculate the centroid. And we kept our fingers crossed and hope that it will come out with that overall geometry. So looking towards the nucleus of our galaxy, they found the following. You're looking at data, and the smooth curve here is the fit to the data. This is data from 4 telescopes around the world, 1 in South Africa, 2 in Australia, and 1 in Chile. Notice each independently, and look how amazingly it matches up with this gravitational fit. This crossing time here is of order a week. And so the idea is to take the model that fits this data, the gravitational lens model. I'll show you the caustic that works. it ends up being a binary system, two stars. The Q is the angular separation between the stars in units of the angular Einstein ring radius. The D, pardon me, and then the Q is the mass ratio. So the model here is fit by this source flying across that caustic there. Notice how close it comes to that cusp. And I'll give you a blow-up of that in a moment. So let's look at it in detail. Here it is. Notice it crosses right there. That's a close-up. This shows you the two images merging. But here is what it comes out. And if you look at that, I mean, the resemblance is just amazing between the two. And we were just excited to see that the actual data giving rise to a model that predicts this geometry for the centroid behavior. And when I'll just leave this final one up, that this is it here in more detail. The different curves here, this would be what you get for a point source, and then these curves that are close to each other are the answers you get, which are essentially the same when you have different brightness profiles for the source. It turns out you can get a similar but different geometry in the case of a cusp, and the equations that you use for this explicit equation, for this explicit curve, it not only gives you a picture, but you can apply that equation to determine the angular radius of the source. And so, and the other things you can do to determine the mass of the lens and other applications. So we would be very surprised if the SIM satellite does not see that. I mean, it better see that, or I think I won't believe the data. Thank you.
Thank you for that beautiful show. Tell. It's really incredible the way that the predictions are realized. Yeah. I'm sure we have time for some questions. Comments? Remarks? Questions?
I have a question. That goes back to the beginning of your talk, where you said that the angles of deflection around a black hole were literature multiples.
That's right.
Could you say a few words?
Definitely. It turns out that, now let's talk about a non-rotating black hole, a Schwarzschild solution. You have a region it's called 3M, near where the light rays come and they loop around the black hole once and comes to the observer. And really, when you're solving the null geodesic equations, you'll find that they're all in 2 pi n solutions. And I remember when first looking at this, feeling very excited because I said, wow, that is nature defining a series. If you look at the angular radius, it's a series of each loop brings the ray in a little closer to 3m. And so it defines an infinite series. And I got excited. I said, is this a new series? What is this? And when I dug deep, it ended up being the geometric series. And so I said, what is a geometric series doing near, in a strong gravitational field of a black hole? But physically, the magnification of the images that loop around drops tremendously with each loop. You can also calculate the centroid due to that black hole, and you could pick up the relativistic corrections. I am interested in this because it's believed there's a massive black hole in the nucleus of our galaxy. And so that would be something big enough, so to speak, where hopefully one can pick up the microlensing signature to test the strong field regime. So far, I don't believe there's any light deflection tests of the strong field regime of general relativity. And so hopefully these things we're talking about, those that loop around the black hole, will give off some kind of testable signature. Yeah. Yes.
Yeah, just want to understand a little bit of the history. Maybe I missed something. You showed this double or triple images that came out of your model, and then you have this data.
That's right.
Look at that. And what was sort of the story? Is the model predicted that data, or the data was observed first, and then the model explained the data? Maybe you can tell a little.
That's right. Thanks for asking that. In this case, the quad systems you're looking at, the data was found. I mean, the data just started accelerating since 1979, and theorists couldn't even begin to keep up. So most of that now is fitting to data. As Professor Spergel's talk later will touch on an area that I'm presently working on called flux anomalies. Remember you saw how the beautiful theorem predicts that bright image pair, that triplet? It turns out they find models that fit the positions of the images like precisely. I mean, you're amazed at the level of accuracy, but they can't fit the flux. So they're saying, what are two images doing so close to each other? You see the source sitting essentially on a fold, but the images don't have the same brightness as predicted by the theorem. And we believe that it's due to dark matter, which will be the topic he's talking about. In a sense, people are saying the dark matter, cold dark matter theory on local scales, meaning galactic scales, is facing a crisis. This may be a way out of it, where you can actually measure the presence of it by saying it's the thing that's causing the violation in the theorem, that these pairs are no longer of equal brightness. Yeah.
No more questions? That's it.
In some ways,
Yeah.
I know Vera Rubin really well. We talked just walking around. But in some ways, I have the feeling, I'm not in this area, that the dark matter was put in to fill deficiencies in equations that really wouldn't fit. Okay? So in other words, Arlie, I'm going to ask you, is it a fudge factor, or is it really there something that you feel? In other words, I'm going to say you can explain it, but I'm not going to be happy with the explanation.
Yeah, well, let me let me respond to that. The way, right, I mean, the question is, sometimes I even wonder if the whole dark matter thing is like ether. You know, it's a spook that's not there, right? And so one takes a position, and by Occam's razor, you sort of go the simplest way out, right? If it turns out that these flux anomalies are not explainable by dark matter in small scales, I think personally I'll start to doubt the dark matter. Because then I don't see how the theory could get out of the crisis on local scales. Yeah. So I may very well be on that other side of the fence. Yes, Carlos.
Different type of question. How did you get interested in relativity? Was it the Mayan sky that you grew up with?
Yes, I tell you, a little boy in Belize, I was telling Juan earlier, a town of about 3,000 people, barely any electricity. And so you just had Mother Nature at you at night. And, as a child, you have all these philosophical questions about how they got there, how they stayed there. And I just couldn't stay away from that.
See, Vera Rubin says the same thing. As a child, she had a big window, and she would just sit there looking and looking and looking. That's exactly the question she started.
Yes, right. Great. Good. Well, thank you. Yeah.